Hello and welcome to another video. So let's do a little bit of recreational programming today and create some music using Haskell. How about that? Sounds like a good idea. Let's create a folder called Haskell Music, and let's actually go there, I suppose. So I want to create a module there, Haskell module, like you know, the regular main.hs module. And obviously I'll need to open that from inside of Emacs, and there you go. To create some music, to create some sound, I would even say, we need to generate some sort of a wave, right? So wave in our case is going to be just a sequence of floats. In that case, it's just going to be a sequence of samples of a sine wave. So we're going to work with the sine wave today. So I'm going to generate like a bunch of, I don't know, samples, starting from 0 up until 48,000, I suppose. And let's map this sequence of numbers with a sine wave, right? So I'm going to open my module with GHCI. And let's take a look at the wave. So here's the wave. It's a sequence of floats. Let's take like, I don't know, 20 numbers out of the wave, and here they are. And the next thing I want to do with this sine wave is I want to actually play it as a sound. To do that, I need to save it to some sort of a format. Today I decided to go with like a raw format because it's the easiest one to generate. You literally take each individual sample here, each individual pulse, and you serialize it into a binary format and you put it into the file. So to do this kind of stuff, to do this kind of like a raw byte, a binary serialization, deserialization, we have a special module in Haskell called data byte string. So it contains a lot of things that collide with existing functions in Prelude, so it's better to import it as qualified. Right, so everything that you import from that module is going to be under some sort of a namespace. In our case, it's going to be just B. So, because for example, it contains something like map, and it collides with existing map that works with lists, and with this kind of qualified import, you're going to refer to it as b.map. Anyway, so it has a very interesting function, and I think that function is located in another module called builder. Yeah, this one is very important. Let's reload everything. That function is called float_le. What this function does, it takes a float, right, and returns you some sort of a builder. And what is that builder? Builder is something that can generate byte strings for you. And what's most importantly, builder is a monoid, which means that if you have several floats and you convert them to builders, then you can merge them together into a single builder and then produce a stream of bytes. So let's give it a try. So in the wave, I should be able to map b float le, and that should give me a list of builders. Just a second, I think it's really inconvenient. I want to start my GHCI inside of TeamUX. I hope I pronounced the name of the program correctly, because that enables me with moving around and select things and highlight things, and I believe this is a like better way to explain things. So specifically what I want to be able to do, I want to be able to do b float le wave, take a look at the type of it and say, here you go, you see it returns a list of builders, right? After that, if I remember correctly, data foldable contains a very useful function that is literally called fold, and it takes a foldable of monoids, and that enables me with folding this entire thing into a single builder, right? To a single builder. So after we have a single builder that represents all of the floats in the sine wave, we should be able to convert it to a byte string. So to do that, we have a function toLazy byte string, right? So you see, it literally takes a byte string and returns you a lazy byte string. So unfortunately, we're not using lazy byte string right now. As far as I know, you have to import this specific module to work with the lazy byte strings. All right, so after that, we should do toLazy byte string. right, to lazy byte string, and there you go. Now we have a byte string. So what we can do with this byte string that basically represents serialized 48,000 floats of a sine wave, we should be able to save it to a file. To do that, we have a function that is literally called writeFile, which accepts the file path, the byte string, and performs some sort of a side effect, I presume saving that byte string to a file. Let's give it a try. So, oh man, let's quickly copy paste this thing. Sometimes history doesn't really work correctly. B writeFile, and where we want to save it? Let's save it to output bin, right? There we go, and let's take a look at the current folder. Here you go, output.bin, 188 kilobytes. 188 kilobytes. We can try to play that thing as a sound using a utility called ffplay. It's a command line utility that comes with ffmpeg, as far as I know. So there's a set of you know, audio and video encoding tools called ffmpeg, and there's a lot of tools there. It's actually pretty good project, and it comes with ffplay that can play raw sound files. But it's kind of dangerous to play this specific sound because it has a very high frequency, right? Because we sample sine wave with the interval of 1 rad, which will produce a very high-pitched sound. So what I want to do here, I want to take samples with a smaller step, and step is going to be like around, let's say, let's actually create a separate variable called step, and the step is going to be like around 100 or something like that. So what we're going to do here, before mapping this with a sine wave, we're simply going to multiply each individual number here with that step. And that will sort of spread the sine wave, right? Because a step became smaller, so the frequency will actually lower a little bit, and maybe we'll be able to hear something. Another dangerous thing about the sine wave is that it modulates from -1 to 1, which produces the sound wave that is pretty loud. So one of the things we can do here, we can also map, after we generated the sine wave, we can map it with some sort of like a factor to lower the volume down. For example, multiply it by half. We can even, you know, do something like volume, like extract that to a separate variable and put it here and multiply by volume. So, and now we have a separate variable that controls the volume of the sound that we're going to produce. Anyway, so let's regenerate and save the sound wave. It's not really convenient to constantly call this sequence of functions all the time when we want to regenerate the wave. So I want to introduce a helper function called save that will basically regenerate the wave and save it to the file for us. So what we're going to do here, we're going to just take this entire stuff and assign to this function, and there you go. So now we can reload this entire thing, call save, and it will regenerate the sound wave. All right, so now we can try to play this sound with ffplay. So let me give it a try. ffplay. As far as I know, to play it with ffplay, first you have to tell ffplay how to interpret that file. The problem with the raw binary sound file is that they don't have any metadata, so the players usually don't even know how to interpret that data. So you have to tell them how to interpret that data. We know for sure that we have floating point numbers there, 32 bits floating point numbers, little endian. So because you see, we're saving them as little endian, right? And after that, we also have to specify the sample rate, right? So what is a sample rate? Basically, a sound wave is some sort of wave, some sort of sound wave, which is can be considered continuous, but I'm not even sure if it's actually like continuous on a physical level. I'm not a physicist, but the problem is that computers cannot store a continuous information. They can only store discrete, you know, separate numbers. And this is exactly how the sound is stored in the computer. So basically, the sound wave is recorded as a set of small samples taken with some sort of interval, regular, or maybe sometimes it could be irregular. I'm not sure. I'm not a sound programmer or anything like that. So, and in sound, there is a notion of a sample rate. So basically, how many samples of the wave value you take per second. How many of them per second? So the usual sample rate, as far as I know, you specify that with the flag AR, is 48,000 samples per second, right? So if you generate 48,000 floating point numbers here, you will basically generate 1 second of the sound. 1 second of the sound. And then we'll have to provide the file, and let's actually try to play it. Let's actually try to play it and see if it would produce any sound. That was actually pretty low sound, but it did in fact produce the sound. I think you make the sound a little bit higher by increasing the step, basically shrinking the wave a little bit and reloading the module and saving it yet again and then running the command. And as you can hear, the sound became a little bit higher. So now we can even control the frequency. But it's not very convenient to, save, like reload module, save the file, and play it with this command. What I want to do, I want to create like a sort of a helper function that will do that, all of that for us automatically. So what it will do, it will save the file and run ffmpeg as a separate process. So how are we going to do that? In Haskell, we have a pretty cool module called system process, right? System process that comes with a very cool function. Let me show you. So it's called run command, which literally takes a shell command and runs it as a separate process. So you can use Haskell as a shell scripting language, so if you want to. So sometimes it's convenient. Okay, so what I want to do after that, I want to take the command that we've been running all the time and run command like that. So we don't need ampersand here, and that should be enough as far as I can tell. So we are repeating the file name 2 times here. So if I'll change that file name ever, I'll have to change it into places. So I want to extract that to a separate variable, something like output file path. Is going to be file path, which by the way is a synonym to integer. So string, not integer. It's a synonym to string, so yeah, it's basically a string. And let's save this thing here, output bin. So, and it also probably makes sense to maybe parameterize save with the file path. So then I can do something like this, file path. I'm going to place it like that, file path. And here I'll pass the output file path. There we go. And here I want to use the output file path, but to do that I need to format the string properly. To format the string, I can use printf, which works like a cprintf, by the way. So then I can just put this thing here, output file path. Probably want to do it like that, and that should be enough. Let's try to recompile it. Okay, so I made a typo here. Okay, there's some sort of a complaint, and the complaint is that run command returns, well, I mean, yeah, the shell didn't pick it up. It returns IO process handle in case you want to do something with the process that was spawned by a run command. But in our case, we return unit. So what we have to do, we have to ignore the result of the run command and then return unit. So if we reload all that, it should work correctly. So now if I do play, it plays the sound. So yeah. And now, if I understand correctly, I should be able to control the frequency. I just have to reload the module and just hit play. And yeah, so it just works automatically. So every time I do any kind of changes, the only thing I have to do is to reload the module and hit play, and it will just produce the sound, which is pretty convenient setup. And this is the setup that we're going to work with. Another interesting thing, so I intentionally put 48,000 numbers here to produce 1 second of the sound, and because we are using 48,000 sample rate. So what I want to do here, I also want to extract that value into a separate global variable so that I can control, and let's call that variable sample rate. Right, it's going to be float, because we're going to do a lot of different arithmetic operations with that sample rate, and let's just save it like that. All right, and here we can do sample rate, and here we can do f sample rate, and that should still work. Okay, so the mod ffplay tries to show and visualize the sound that is playing, but it's showing it in a very boring mode. As far as I know, ffplay has a very interesting mode, show mode, that shows the actual sine wave that it's playing. Yeah, it's called show mode 1. So let's actually put show mode 1 there, reload the module and play it. Yeah, there you go. So this is literally the sine wave that we generated. So to get the idea of the scale we're working with, so we generated a bunch of samples for the sine wave, right? And where do you think, what is the size of a single sample on this picture that we generated? Think about it. We're generating 48,000 numbers per second of the sound. So a single sample is probably around of 1 pixel right there, or even smaller, I would say. So that's the scale we're working at. Probably. I'm not sure if it interpolates them, maybe it doesn't, but as far as I know, that's the scale we're working with. We're generating a sine wave with a very fine resolution, with a very small fine resolution. We're sort of carving that sine wave, that sine sound wave out of the pixels. So that's why the sample rate is so high, 48,000 per second. Yeah. And what's interesting is that we need to generate this amount of samples for a single second, which means if you want to play 2 seconds of the sound, you have to multiply this by 2, right? So there was 2 seconds. And furthermore, you can extract this like duration to some sort of like a separate variable and control it. For example, if you want to play not just 2 seconds, but maybe half of a second, and it will still work. That was pretty quick. So it's half of a second. That's what it is. And we're going to have a lot of different measure units here, and most of them are going to be floats. So to simplify keeping track of what we're talking about, I think I want to introduce type aliases. For example, for the duration, we're going to use seconds. So I'm going to introduce a type alias type seconds, which is going to be equal to just float. And we're going to say that duration is in seconds. So the sample rate itself is going to be have type samples, right? So the sample rate is going to be samples. So you see here what we're doing. We're multiplying samples by seconds, right? So, and we get the amount of samples we have to generate to produce duration amount of seconds, right? Make sense? Hopefully that makes sense. Okay, that's pretty cool and all. But the question is, like, we can sort of control the frequency, but how can we generate a very specific frequency? Like, for example, I want to generate a frequency that is called pitch standard. So let's Google that. Pitch standard. So there's this interesting frequency that is called pitch standard. It's 440 Hertz, right? So 440 Hertz, which represents the note A in 4th octave, I suppose. I'm not a musician, I don't know much, but it's really a standard pitch. It even has its own ISO 16. Yes. how can we generate the pitch standard? We know that the frequency of pitch standard is 440 Hertz, and since we're starting to work with Hertz, let's introduce the type alias for Hertz. Let's call it HZ. So how can we generate 440 Hertz in our case? Well, what is Hertz in the first place, right? So what is that measure unit? So basically it says how many times per second something will happen, right? It doesn't really answer what exactly, it's just something. So in our case, something should happen 440 times per second, but what? So in case of a sine wave, we have to perform 440 cycles of a sine wave per second. What is a single cycle? A single cycle with sine wave is going to be starting from 0, going up until 1, then going back to 0, and then going below 0 and going back to 0. So it's a single, cycle of a sine wave, right? Cycle of a sine wave. So if we have sine x, a single cycle of a sine wave happens between 0 and 2 pi. So this is a single cycle of a sine wave. So, which means that we have to perform 440 2 pi's per second. So this is what we'll have to do, right? We'll have to perform 442 pi's per second. But what should this step be equal to perform 442 pi's per second? Well, we already know that we have to take 48,000 samples per second, right? So this is a single second, and we have to take 48,000 samples per second. So if we divide this entire thing by the sample rate, we will get this step with which we have to, step and take samples to produce 440 Hertz, basically the pitch standard. So, and by the way, I should probably use HZ here because it's the variable that we introduce here, right? All right, so let's try to compile that and see if it compiles. It in fact compiles, and let's listen to the pitch standard. So that was actually pretty quick. Let's make it a little bit longer. Let's make it like 2 seconds. Is it really a pitch standard? I'm not really sure. I don't really have a, how is that called? Like perfect pitch? I can't hear that. So let's actually Google up the pitch standard on YouTube and listen to it and compare how they sound. Okay. Pitch standard 440 Hertz. Here it is. Let's listen to it. This is it. This is actually it. So now we can even control not only duration and volume, but also the frequency with which we can play sound, which already enough to produce melodies. This is actually pretty cool. So let's actually extract this entire stuff into a separate function. I want to call this function frequency, which takes Hertz, seconds, and produces the sound wave. So I want to introduce like a type alias for this kind of flow that represents a single sample of the sound wave. So as far as I know, that single sample of the sound wave is called pulse, but I'm not 100% sure on that. So if I'm kind of wrong, please correct me. But I do know that there is a thing called PCM, and as a matter of fact, we're generating a PCM file. So it's basically it stands for pulse code modulation. So we're generating pulse code modulation file, and each individual samples there is just a single pulse. So because of that, so to keep track of what we're talking about, I want to introduce a type alias called pulse, and it's also going to be float. Okay, so we're producing a sequence of pulses, and wave is also a sequence of pulses. And yeah, everything seems to be okay. All right, so what I'm going to do here, I'm going to take Hertz duration and take this entire stuff and just straight up, let's say move it there. So right now Hertz and duration are parameterized through the arguments, and now I can generate frequency with Hz and duration. So the reason why I wanted to separate this function is, so I forgot where, is so I can generate several nodes together. For example, so the first node is going to be 440 Hertz. Let's play it for half of a second. And I want to, after that, play another node with a different frequency. For example, let's say frequency 540 Hertz. I'm not sure if it represents actual node on the standard scale or anything, but yeah, I want to do something like that. The problem is, wave is supposed to be a sequence of pulses, and frequency function returns a sequence of pulses as well. So if we do things like that, we're gonna get a sequence of pulses, and that's not gonna compile. So we need to flatten it out. We have a function that is called concat. It takes a sequence of lists and basically concatenates them together. So if I concat these two things together, I'll have a sound that first plays 440 Hertz for half of a second, and then 540 Hertz for half of a second. Maybe it's too fast because it's going to be a single second. Let's actually play them for 1 second. So each individual note will be played for 1 second. Let's reload all of that and let's play it. Did you hear that? Did you hear that? I think it was actually pretty epic. So furthermore, with this kind of setup, we can even generate nodes. For example, what we can do, we can take a sequence starting from 0 to 10, let's say, right? And we can use some sort of list comprehension, and here's going to be our number of a node. And here we can do the following thing. We can take the pitch standard. So we keep talking about like the pitch standard. I think it makes sense to introduce like a global variable for the pitch standard. Pitch standard, it's in Hertz, we know that, 440. So then we take the pitch standard and we add I multiplied by 100 to it. So it's not like an actual scale, like because scale is not linear. We're generating notes linearly, but they don't really grow linearly. Like at least semitones, they are not linear for sure. And we're going to go to that a little bit later. And then we're going to have some sort of a duration. And let's say the duration, each individual duration is going to be like 1 second of some sort. And after that, we can just simply concatenate this entire thing. So as you can see, we can generate 10 nodes using this kind of setup. Let's see if it compiles. It does compile, and let's listen to that. And that will continue like 10 times. So I actually cut it because it's going to go for 10 seconds. But you get the idea. So it's pretty cool. It's pretty cool. But again, as I mentioned, semitones in notes, they don't grow linearly. As a matter of fact, there's a special formula that lets you take semitones, basically the amount of semitones deviation from the standard pitch, and give you the frequency in Hertz that you have to play for that specific note. So what I'm talking about is, let's Google something like note frequency formula. As you can see, I already Googled it up, so I already researched this topic. And there's this page that I'm going to link in the description. It's actually a pretty cool page, which gives you the table of nodes and their corresponding frequencies, and even the wavelength, if we want to know that. And there was a formula somewhere. I'm not really sure where is it. So form, I think it's not on that page. I think it's on a different page. Here it is. Here is the formula. This is the only thing we need to know. So n is the amount of semitones that deviate from the standard pitch. F0 is the standard pitch, and a to the power of n is a special magical number. So a is equal to the 12th root of 2, the number of which when multiplied by itself 12 times equals to this thing. So basically we don't really have to understand this formula to use it. We can just treat it as a black box that we feed amount of semitones into, and it gives back the frequency. So let's actually try to implement that formula. So I'm going to define the function that accepts the amount of semitones, which can be negative, by the way. I think I'm going to use float, so I don't have to convert between integers and float, because in Haskell it's kind of annoying because it's, you know, very strongly typed and stuff. So this is the amount of semitones. You know what, since I'm talking about semitones, maybe it makes sense to introduce the type alias semitones, which is going to be float. So function takes the amount of semitones and returns Hertz. And this is exactly what this function does. You see, it's super convenient to have these kind of aliases. You can clearly see what the functions, like the intent of the function, so let's even say. So it's going to be n, and what are we doing here? So we need to calculate 2 to the 12th root of 2. So in Haskell, we can easily do that by rising 2 to the power of 1 over 12, and this is the number that we're gonna get. Right. So then we have to rise that thing to the power of n as described in the formula, you see. And after that we have to multiply this entire stuff by the pitch standard. All right. So I'm going to reload everything, and let's check this formula. So for F0, it should return as pitch standard. For 1 semitone higher, it returns 466 something something after the period. And let's actually compare that with the stuff in the table. So 440. So the next node after A should be 466.16, and we're pretty close. With F2, it should be equal to 493, 483.88. So it actually produces correctly. So now let's introduce another function called node. It's going to be very similar to frequency, but instead of hertz, it's going to take semitones. You see, it's going to take semitones, seconds, and produce the sequence of pulses. So it's going to be n, duration, and it's going to be implemented in terms of frequency function, which is super easy to implement. You just use f function that maps your semitones to hertz, and that's pretty much it. So now, instead of talking about frequencies, we're talking about semitones of the notes, which is more convenient if you want to, you know, compose the actual music. Right, so, and now let's not generate frequencies, let's generate actual semitones. So I'm gonna do note I, and let's listen to the semitones, shall we? Sounds like semitones, and I think if we multiply this entire thing by 2, we're gonna have like an actual tones. Sounds like tones. Maybe we should also play some sort of like a major scale. Let me try to generate that. So duration is 1 second. I think it's too slow. Let's actually have like a half of a second. And how does it start? How does it start? So we're gonna start with 0. The next one is full tone, if I remember correctly, which is 2 semitones. Then another tone. And after that goes half of a tone, then full tone, another full tone, and another full tone, and then semitone. I hope I didn't make any mistake here. If I did, please tell me in the comments below. If I made any kind of mistake, I think I will be able to hear it. Sounds like a major scale, I suppose. Yes. So we can actually, you know, produce some sort of notes. Okay, and there's a problem with this kind of setup that we have. Let's try to play the same note several times, like at least 5 times. Right. It sounds like a single note, right? This is the problem. This is actual problem. Like it sounds like a single note. And this is because there's no time separation between them, right? We can put a little bit of silence between the notes, but that would create like a clipping noise that is not really pleasant to listen to. So what I want to do is I want to implement some sort of like attack and release for each individual note. I think it's usually called like attack, decay, release system or whatever. I'm not a musician, so I know nothing about this kind of stuff. So, but this is basically what I want to implement. Yeah, basically for each individual note, we're gonna start the volume from 0 to some particular point. Then people usually implement some sort of decay, and then they keep the volume, you know, sustained for quite some time, and then they release the volume by dropping it down over time. So I don't know why it is implemented exactly like that. Maybe it's for, you know, it's pleasant to listen to when there is like sort of like a bounce of the volume. I have no idea. Again, I'm not a musician, but I think we're going to implement only attack and release, and we're going to just sustain at a particular level for the entirety of the note. So, and that will give some sort of like a little bit of separation between the notes, and the separate notes are going to be at least distinguishable, which is good for playing melodies and stuff like that. Okay, so how are we going to do that? This one is very interesting. So in the frequency function, we're generating pulses for the actual wave, right? So let's save those pulses to a separate variable called output. So the output is a sequence of pulses, and here it is. All right, so to implement attack, we need to generate another sequence of pulses, right? That starts with 0, then increments with a particular step, grows a little bit, and then stays at 1 for the entirety of the whole note. So I think the easiest way to implement this kind of thing is going to be just generating an infinite list with a step of 100s, and mapping this entire thing with something like minimum between x and 1, so it doesn't grow over 1, because if you're gonna generate like an infinite list like that, it's gonna definitely go over 1. I can even demonstrate you, like I'm gonna take like 200, I suppose, and I couldn't do that for some reason because I put as comma here. Yeah, and at some point it will starts to go over 1, and we don't want to do that because the modulation is happening like between -1 and 1, and each individual sample of the attack here represents the volume, right? It represents the volume of that output sound that we want to have. But by the way, if we swap these arguments like that, I should be able to apply eta reduction here and make this entire thing a little bit simpler. So after we produce the sequence of volumes for each individual pulse of the output, we have to merge them together. So basically we have to multiply the corresponding pulses to apply the volume, the same way we apply the sort of master volume to the whole output. So we're going to do that with the function zip width, which accepts a function that a binary operation and two lists, and basically, you know, zips these two lists together. So basically, if you had two lists like that, right, and you zipped them with multiplication operation, you would get something like this. So you see it went through each element of both of the lists and multiply the corresponding elements. And this is basically what we want to do here. So we're going to do zip with attack and output, and of course something like that. So this is what we want to do. Let's try to hear how it sounds like. I wonder if it's going to sound good or not. Okay, so this is the comma, and let's play it again. Okay, you can kind of hear distinct notes, but not that much. So I think if we increment the step like 1,000s, it's going to be even better, I think. All right, and there's still clip at the end of the notes, and this is because we don't have any kind of release, right? We don't have any kind of release. So the easiest way to implement release is to just take a tag and reverse it and zip it again. So yeah, so we're gonna have a release as a sequence of pulses, and the problem is that we cannot really reverse attack. We cannot do that because attack is an infinite list, right? And the only reason why we can zip within infinite list is that because we're utilizing because we're utilizing the laziness of the language. So let me demonstrate you. So imagine that you have a finite list from 1 to 5 and an infinite list from 1, and you're trying to zip them. So what's going to happen? You're going to end up with the list that is equal to the length to the shortest one, because the rest of the infinite list was cut out. So this is the laziness of the language. Since you didn't use all of the elements of the infinite list, the rest of the elements of the infinite list did not calculate. And this is basically what we're utilizing here. Output is finite, attack is infinite, we zip them together and we get the list that is equal to the output, because it's the shortest one, because it's shorter than an infinite list, obviously. But you cannot reverse an infinite list, because you have to calculate the whole list to reverse it. So what we have to do in this particular case, I think we have to cut the attack list to the length of the whole output. That's what we need to do. I wonder if we can actually do that, like take the length of the output, like literally. Yeah, take the length of the output, reverse it, and then we have to zip release along with attack and output. We cannot use zip width to do that because it takes 2 lists and we have 3 lists. Guess which function we have to use to zip 3 lists? I think for that we need to import something like import data list. So that function is called zip with 3. So if you need to zip 4 lists, guess which function you have to call. I don't know how many of them. Can I zip 8? I think it goes up until, yeah, it goes up until 6. So after 6, maybe you have 7. Yeah, you have 7. Yeah. So you can only zip up until 7 lists, unfortunately, in Haskell. You know, see, a very powerful type system. Anyway, so what we're gonna do here, we're gonna zip with function that takes 3 arguments and multiplies them together. And we're gonna zip together a release and attack. Yep. So this is how we're going to do that. We're generating attack as an infinite list, starting from 0 with a particular step, and we cup each individual volume there to 1. Then release is basically attack, but reversed. But since attack is infinite, we have to cut attack to the length of the output, and then we're going to reverse it. So yeah, the release is going to be 1 up until the end, and at the end is going to drop. So you see, attack and release in our particular case are symmetrical. And yeah, then we just, you know, merge everything together, zip everything together. So unfortunately, formatting, you know, removed the separation. And yeah, so this has to be called zip3, zip with 3. Let's reload everything and let's try to play it. And now you can hear there's a very smooth separation between the notes. And look at the waveform. You see, this is exactly what I'm talking about. You see, this is the release. You can see how the volume sort of drops down to 0. So yeah, and there's a very smooth separation between the notes. All right, I'm really happy with what we have right now. Okay, so, but when we talk about notes, we don't really want to talk about duration of notes in terms of seconds. It is not convenient. So the same way it's not convenient to talk about notes in terms of frequencies, the same way we don't talk about notes in terms of seconds, we talk about notes in terms of beats. So in music, we have a notion of tempo, right? And tempo is usually described in beats per minute. Yes, so a particular song usually have a particular BPM, like 90 BPM on 120 BPM, and that means beats per minute. So since we're starting talking about beats, let's introduce type called beats, which is also going to be float. And let's have a global variable that is called BPM. So let's put it somewhere here. BPM, it's beats And it's, in our case, let's say it's going to be equal to 120, right? And what I want to do, I want to refactor function node to take beats this node have to play according to the current BPM. All right, so this is the beats. And to convert beats to seconds, we have to know the duration of a single beat. So we're going to take beats multiplied by beat duration. So, and beat duration depends on BPM, obviously. And since it's a duration, it's in seconds. So BPM is beats per minute. We need to convert that to seconds. How many seconds we have in a minute? We have 60 seconds in a minute. How many beats per minute we have? We have BPM beats per minute. We divide them together and we get amount of seconds in a single beat. There you go. Now, in a note, this is not seconds anymore. This is the amount of beats. So if I say that I want to play each individual note in a single beat, I'll have to provide one, and let's hear that. So this is 120 BPM, right? Let's actually try to play each individual note not in one beat, but in a half of a beat, right? All right. How about a quarter of the beat? Let's reload everything. What if the last one is going to be half of a beat? All right, this one is interesting. So, okay. Ta-ta, 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 ta. Okay. I think this one is actually kind of redundant. Let me try to do that one there. Okay. So what if we repeat this entire section and write it to 5 semitones? I think that would be actually pretty good. All right, what's the next part? What's the next part? I think it's down to a tone, but I'm not quite sure. So I'm doing all of that by ear, so... yeah. And at that point, I think we're going down like below the pitch standard, but I don't know how low, maybe -1 or -2. I think like a whole tone. Let's reload everything. Yeah, it has to be like a 1 beat to... yeah, something like this. Yeah, and there's yeah, you get the idea. You get the idea. Yeah, you can continue like indefinitely, but you basically can now play music with Haskell.